Humans have a relatively firm understanding of how the universe works. For a species that hasn't left the orbit of our planet, we seem to know a lot about how the rest of the universe functions. But most of this knowledge is based on theories and assumptions, which is why space probes like Voyager 1 are crucial to our knowledge of the cosmos. These space probes send us data in real time, giving us information on the outer regions of our solar system that we might not explore ourselves for decades to come. So what happens when a space probe we've depended on for decades for valuable data starts sending strange signals and terrifying data? Scientists recently found themselves in disbelief at the string of terrifying signals sent back by Voyager 1. But what do these strange signals mean, and how do they affect the future of Voyager's space exploration? To find that out and more, stick with us as we take a look through Voyager's terrifying signal hiccup. The Voyager space probes have been part of humanity's effort to study the outer planets since the 70s. Although they were not the first of such missions, the Voyagers were designed to explore further out into our solar system using information from veteran space probes such as the Pioneer 10 spacecraft. The Voyager space probes were designed to be more effective at handling the intense radioactive environment around massive planets such as Jupiter and Saturn. The initial mission plans were intended to perform flybys around both planets to give us detailed imagery of the two largest planets in our solar system. Constructed at NASA's Jet Propulsion Laboratory, Voyager 1 was built with several instruments and components, making it an unprecedented piece of space technology. The probe was built with an impressive communication system which was designed to be functional even beyond the limits of our solar system. Some of these instruments included a Cassegrain 12-foot antenna which the probe uses in sending and receiving radio waves through NASA's Deep Space Network. NASA had specifically designed its deep space network with communications facilities at 3 key locations around the world. These facilities were located in the United States, Australia, and Spain, were strategically placed such that scientists would be able to receive signals from the Voyager space probes irrespective of the angle of the Earth's rotation. Taking into account the uncharted regions of deep space and its effect on signal transmission, Voyager was built with a digital tape recorder, able to record up to 67 megabytes of data in the event the probe is unable to transmit a signal at a particular time. This saved data would then be transmitted subsequently at another time when the probe is able to establish a direct line of transmission to Earth. Voyager is also built with the volatile nature of space factored in to its internal systems. Voyager 1 is built with 3-axis stabilization gyroscopes, 16 high hydrazine thrusters, and a computerized referencing instrument, all working together to keep the probe's radio antenna pointed toward Earth. These components are important because the outer edge of our solar system is filled with volatile and unpredictable radioactive particles that move at high speeds which may knock Voyager out of its desired position. These instruments enable the probe to realign its antenna position whenever it encounters such conditions on its journey. Being able to send signals back to Earth is one thing, but keeping these instruments powered up and working through decades of traveling the solar system involves a near-constant supply of power. Previous probes sent out into space have all been equipped with solar panels used in harnessing solar energy needed to power the onboard systems and equipment, but Voyager was the exception. With the anticipation that Voyager would travel the far reaches of our solar system where sunlight was unable to sufficiently reach any solar panels, engineers over at NASA built Voyager with a different power source instead. Built into Voyager's structure are 3 radioisotope thermoelectric generators, or RTGs. These RTGs each contain 24 pressed spheres of plutonium-238, which was a stellar fuel choice because each sphere had a half-life of 87 years and slowly degraded over time. This degradation would give off heat, which would then be converted to electrical energy needed to power the systems and components of Voyager 1. At the start of Voyager 1's journey in 1977, the RTGs generated about 470 watts of electricity, a number which has reduced by almost 50% over the 45-year journey of the space probe. But despite the recent strange signals that have been observed by scientists, Voyager 1 has been reliable from day one and has done a marvelous job of showing us the intricate parts of the planets within our very own solar system. Upon launching from Earth in September of 1977, Voyager made the trip beyond our red neighbor Mars and onward to its first primary target, Jupiter. Reaching the giant planet on the 5th of March 1979, Voyager 1 began a detailed observation of the Jovian system by studying the planet's magnetic fields, moons, rings, and its hyperactive radiation belt. The probe made its closest flyby of Jupiter at a distance of about 217,000 miles from the planet's core, and this allowed for a much more detailed photographic resolution than we've ever seen. During a crucial 48-hour period in which the probe toggled on Jupiter's gravitational pull, Voyager 1 gave us the very first close-up imagery of Jupiter's Great Red Spot, a massive anticyclonic dust storm larger in size than the Earth. Another key feature observed by Voyager 1 as it orbited Jupiter was the discovery of volcanic activity on the surface of Io, one of Jupiter's primary moons. This marked the very first record of volcanic activity anywhere else other than the Earth in the solar system. But that wasn't all. It turned out the volcanic activity in Io affected not just its own surface, but the entire Jovian system as well. When Voyager 1 sent back data on the observations of Io, scientists were shocked to find that despite the hot volcanic eruptions of the moon, it has an extremely cold surface. It turns out the moon had no atmosphere and was therefore unable to trap any of the heat it was erupting, resulting in a cold surface with temperatures reaching -202 degrees Fahrenheit. The Jupiter flyby also gave the first glimpse of the smooth, uncratered surface of Europa and found an icy surface that could very well hold liquid water underneath the surface. Voyager 1 also gave us the very first detailed pictures of the largest moon in the solar system, Ganymede. With a massive diameter of over 5,200 kilometers, Ganymede is about 26% larger than Mercury by volume and even more so than Pluto, making it the 8th largest object in our solar system, not including the Sun. With data relayed by Voyager 1, scientists were able to tell that not only is Ganymede one of the oldest moons in the solar system, but it's even older than the Earth itself. After successfully completing its detailed observation of Jupiter and its moons, Voyager 1 proceeded to carry out a gravitational assist using the planet's gravity to increase its velocity. Voyager 1 was able to slingshot to its next target planet, Saturn, which it reached in November of 1980. Achieving the very first flyby, Voyager 1 was able to get within 124,000 kilometers of Saturn's surface, where its onboard cameras observed the complex structures of the planet's rings as well as the active state of its atmosphere. Scientists had always known that the surface of Saturn was plagued with high winds, but when Voyager 1 signaled back data from its observations, they were shocked to find that wind speeds on the planet exceeded expectations. The data indicated that Saturn has wind speeds of up to 1,100 miles per hour, dwarfing the highest 400 miles per hour wind speeds recorded on Earth. Voyager 1 also signaled back data from its observations of the moons orbiting Saturn, most notably the Earth-like moon Titan. Titan had previously been observed using telescopes, but with observations from Voyager 1, scientists were able to get the very first close-up pictures of the moon's surface, showcasing its thick haze atmosphere. With Voyager 1's measurements of the moon's atmospheric conditions, scientists speculate that there could very well be lakes of liquid hydrocarbons which evaporated to form the thick clouds that shrouded the surface of Titan. Voyager 1's observations of Titan were a crucial part of the mission, as it was vital to study the only other body ever observed to possess stable bodies of liquid hydrocarbons similar to Earth's. This was the major contributing factor to Voyager's trajectory, so much so that had Voyager 1 been unable to perform a Titan flyby for any reason, Voyager 2's trajectory would have been immediately adjusted to perform the flyby before continuing to Uranus and Neptune. Fortunately, Voyager 1 was able to perform the observations and proceeded to observe Saturn's other moons, including Tethys, Hyperion, Enceladus, and Rhea. Rounding up its observations, Voyager 1 began to make its way to the edge of the solar system, performing one last gravity assist using Saturn's gravity to increase its velocity. While Voyager 1 made its way toward the outer edge of the solar system, it had begun to lose small amounts of energy, something scientists had predicted, and it became necessary to start deactivating non-essential components that the probe could do without at this point in its mission. While it became apparent that the cameras would be the next component to be deactivated, Voyager 1 took one last series of pictures of the solar system as seen from the outer edge. These pictures became known as the family portrait, with its most notable image being a picture of Earth seen as the pale blue dot. This image really put into perspective our place in the universe and further emphasized the importance of the Voyager missions. So after the family portrait, the cameras on Voyager 2 were deactivated with only essential computers and sensors left running. By February of 1998, Voyager 1 had reached a milestone distance of 69 astronomical units, which is the equivalent of 6.4 billion miles from the Sun. This was a point in space that only one other spacecraft in history had reached, the Pioneer 10 spacecraft, and Voyager exceeded the mark, pushing onward to interstellar space. While Voyager 1 no longer had its imaging system to send imagery of the solar system, it still had other vital components, such as its plasma wave subsystem, which it used in studying wave particles and their behavior, a study that would prove to be vital as the probe encountered the termination shock. After flying for a few years with no significant data changes or usual signals, scientists received telemetry data in February of 2004, which indicated that solar winds originating from the Sun had slowed to subsonic speeds. This led to the conclusion that Voyager 1 had entered the termination shock. This was a point at the beginning of the edge of the solar system where the solar winds slowed to subsonic speeds as a result of their interaction and collisions with the interstellar medium. This interaction was detected by Voyager 1 as it caused significant compression and distortion to the magnetic field surrounding the space probe. The termination shock was merely an astronomy concept at that point, but with Voyager's readings, scientists were able to establish a definitive boundary, and it is believed the termination shock lies between 11 to 13 billion kilometers from the Sun. Voyager 1 crossed the boundaries of the termination shock in late 2004 and proceeded to an uncharted part of the outer solar system where solar winds not only slowed to subsonic speeds, but equaled the external pressure from interstellar cosmic radiation. This point of Voyager 1's journey marked the beginning of the heliosheath, a region of space where the radial outflow of solar winds could no longer push against the inflow of cosmic radiation. At this point, Voyager 1 was approximately 10.8 billion miles away from the Sun. At this distance from the Sun, solar winds were observed to be at zero, indicating that interstellar winds pushing against the heliosphere caused them to turn sideways and therefore unable to move forward. This was confirmed by mission controllers over at NASA on December 13, 2010, as Voyager 1 sent back signals containing data observed by its cosmic ray system. This system has been in the space probe from the very beginning of its journey, but didn't see much use as the level of cosmic radiation inside the solar system was of no consequence to its mission. But at the heliosheath, Voyager 1 began detecting increasing amounts of cosmic radiation, which scientists were now able to study the acceleration, origin, and life history of these rays to further understand them. Because Voyager 1 was moving beyond the point where it could observe solar winds, mission controllers over at NASA commanded the spacecraft to change its orientation in order to measure the sideways motion of these solar winds. This was carried out in March of 2011, in which a practice roll was carried out to test the spacecraft's ability to reorient and change its position. This, of course, did not alter the spacecraft's course, but only tilted its axis 70 degrees clockwise with respect to the Earth in order to detect the sideways movement of solar winds. This was the first maneuver carried out on the spacecraft in about 20 years since the family portrait was taken back in 1990. After the observation was successfully completed, Voyager 1 reoriented itself using Alpha Centauri as its guide star and resumed transmission back to Earth. Later on, in 2011, NASA announced that Voyager 1 has detected the very first Lyman alpha radiation originating from the outer reaches of the Milky Way galaxy. Lyman alpha radiation had previously been detected emanating from other galaxies, but due to the protective barrier of the heliosphere, it was nearly impossible to study these particles until now. At this point in Voyager 1's journey, NASA revealed that the space probe had encountered a region of outer space referred to as cosmic purgatory. In this region, solar particles emanating from the Sun are practically non-existent, but instead, the magnetic field produced by the solar system doubled in strength. This was a response to the outer pressure applied by cosmic radiation and was simply our solar system's way of protecting itself from these volatile cosmic particles. At this point in space, high-energy electrons emanating from outside the solar system and other parts of the galaxy had increased more than 100 times the initial amount observed inside the solar system. This region lies approximately 113 astronomical units from the Sun, meaning Voyager 1 had very well begun its exit from the edge of our solar system and was now entering interstellar space. In June 2012, NASA announced that Voyager 1 was detecting drastic changes in the environment with respect to an increased number of charged particles and cosmic rays. This indicated the inner edge of the hemisphere, making Voyager 1 the very first spacecraft to cross into interstellar space at a distance of 121 astronomical units from the Sun. At this point in the Voyager 1's journey, it was extremely fortunate that the probe did not depend on solar energy as a power source, as sunlight took over 16 hours to reach Voyager 1. At this distance, Voyager 1 was traveling at a speed of over 10 miles per second respective to the Sun. At its current speed, Voyager would need approximately 17,565 years to travel 1 light-year. At these speeds, it will take Voyager 1 over 73,000 years to reach the closest star to the Sun, Proxima Centauri, which is about 4.2 light-years away. But Voyager 1 isn't headed for Proxima Centauri and is instead headed in a different direction, making a straight line the constellation of Eucus. Mission controllers over at NASA reported in 2012 that Voyager 1 was detecting heavy collisions with high-energy particles. These particles were thought to be cosmic rays originating from exploding supernovas well beyond the reaches of our solar system. This increase in high-energy particles was also followed by a drastic drop in low-energy particles which originated from the Sun. Scientists at Johns Hopkins University stated that these two occurrences were sufficient enough to declare that Voyager 1 has fully exited the heliosphere and was now in interstellar space. But then scientists observed something unexpected in the data, as it appeared that the magnetic properties of this region were different than had previously been anticipated. This led Voyager project scientist over at California Institute of Technology, Dr. Ed Stone, to release a statement stating, "Voyager has discovered a new region of the heliosphere that we had not realized was there. We're still inside apparently, but the magnetic field now is connected to the outside. So it's like a highway letting particles in and out." This strange occurrence with the magnetic field indicated that the region was 10 times more intense than scientists had initially theorized. It was expected to be the last barrier that needed to be overcome before Voyager 1 would have completely exited the solar system and was now fully in interstellar space. With Voyager 1 fully in interstellar space since 2012, scientists have been monitoring its signal feedback with high anticipation, seeing as how no spacecraft has ever made it beyond the heliosphere in the history of mankind in space exploration. But they were shocked when during one observation cycle, Voyager 1 began sending unknown and frankly terrifying data. The data received from Voyager 1 appeared to be generating random data which reflected fairly impossible scenarios that were unlikely in interstellar space. NASA's Jet Propulsion Laboratory officials revealed that the unexplained data was originating from Voyager 1's Altitude Articulation and Control System, also known as AACS. The system was in charge of measuring and calculating the orientation of Voyager 1 and its antenna, keeping the probe on a direct line to Earth for proper signal transmission and orientation. Scientists were at a loss at the cause of this terrifying signal and junk data sent back by Voyager 1. This was because the probe appeared to be functioning properly, as it was still able to observe, gather, and send data back to mission control here on Earth, although the data received was basically unusable. At this point in the mission, both Voyager 1 and 2 were nearly 45 years old, a lifespan that was far beyond the original mission expectations. However, during the entire mission, both Voyager 1 and 2 had consistently sent back accurate and readable data, despite having several systems deactivated to conserve power. Voyager 1 is currently 14.5 billion miles away from the Earth, and at this point, signal exchange between the probe and mission controllers at NASA is a huge delay, it takes over 22 hours for signals from Voyager 1 to reach Earth and roughly the same amount of time for signals to be sent back to the probe. After grasping at straws for weeks trying to solve the mystery of the strange signals sent back by Voyager 1, mission controllers over at NASA recently found the root cause of the problem. They discovered that Voyager 1's AACS, which is responsible for keeping the probe's antenna always pointed toward the Earth, had encountered a problem. The system began sending information through a corrupted computer that had been deactivated years ago. The data in itself was accurate and readable, but being relayed through a corrupted computer inadvertently corrupted the data as well, therefore sending the junk telemetry data back to Earth. According to NASA, once they discovered the root cause of the problem, they only had to send a new command to Voyager 1 instructing the probe to stop sending data to the corrupted computer and resume using its functioning computer instead. NASA reported that this was a quick fix and that Voyager 1 is now back to sending accurate data about its current observations of interstellar space. However, scientists are still unable to account for the reason why Voyager 1 began using the corrupted computer when they sent no commands to do so. It has been widely speculated in the scientific community that Voyager 1 probably encountered some form of cosmic radiation containing charged particles which distorted system commands, causing the switch to the corrupted computer. This is still just a theory, as NASA is yet to give an account of what they believe was the cause of the system malfunction. And while mission controllers believe this was an isolated incident, there has been wide speculation that the likelihood of a similar situation happening again is highly possible due to the unknown nature of interstellar space. And while Voyager 1 has been in interstellar space much longer, Voyager 2 recently entered the region of space in 2018 and may very well encounter the same problem soon enough. Voyager 1 has played a crucial part in our understanding of the planets in our solar system, as well as the heliosphere, which up until now was merely a theoretical concept. Initially built to last just 5 years, Voyager 1 and 2 are both 45 years old, with mission controllers confident they'll be able to extend the life expectancy of both probes well into 2025. Voyager 1 will still be able to send back data until its power source runs out in the next 3 years. But that won't mark the end of Voyager 1's journey through the galaxy. The space probe is expected to continue with its current velocity and enter into the Oort cloud in some 300 years' time. Anticipating that the space probe will float through space for hundreds of thousands of years to come, Mission Control added the golden record within the structure of Voyager 1. This record contains several messages, including a child's voice, recordings of various musicians, and greetings in 55 different languages. So in the unlikely event that Voyager 1 encounters aliens, they will get a glimpse of what life on Earth sounds like. Do you really think Voyager 1 will encounter something unexplainable in interstellar space? Let us know in the comments, and we'll see you next time.